Right, hello Year 9. So today what we are going to be doing is continuing with our work on um, basically science skills, investigative science skills. So the first thing I would like you to do is in assignments there is a Word document which is basically a copy of this. What I would like you to try and do is link the word with the correct answer. Okay, so the correct definition. So you've got the word. What do the words actually mean? Okay, so have a go at that, and then what I will do is after I've talked you through this part of the lesson, we'll go through the answer at the end. So pause the video and give that a try now. Might be a good idea to do it in pencil first, just in case you do make any mistakes. The first one has been done for you. So, for example, a zero error is when your equipment isn't zeroed properly. So what that might mean is if, say, for example, you're weighing something on a set of scales, you put, and before you've even put anything on it, it reads, say, like 10 grams. Okay. What would we, that means it hasn't zeroed properly. So what could we do about that? So you need to start thinking logically. But try and think about the other ones. Some are quite obvious. Some you might have to work out by process of elimination. Some you might have to look up. Okay, so I reckon it'll probably take you about 10 minutes or so to work this out. Okay, so give it a go and see how you get on. Okay, year 9, welcome back. So the next thing that you should be doing is you will see that in the post I've uploaded a photo of page 5 in the physics revision guide. Now, this is actually the same across all the revision guides, so it's necessary for biology, chemistry, and physics, and for those of you doing triple and non-triple next year. So basically, what it does is it outlines this page, what these words actually mean. So, what I would like to do is make a few notes on that and pay particular attention to the bits which are highlighted in bold or coloured or underlined. Okay, so there's blue, green, and orange. Really make sure you understand what these words mean because these are the kind of things you'll be tested on across all 3 papers. So you've got a choice here. You can add to your definitions, um, which you've got here, or you can do your own separate definitions. If you print it off the sheet, it might be a good idea to add them to the sheet next to the boxes. So, for example, a zero error, which you've got there, you could have I'm just trying to find it. Yeah, I think it's in the bit which is orange. Talks about random errors, systematic errors, a zero error. So, for example, just to make things more complicated, if a systematic error is caused by using equipment that isn't zeroed properly, it's called a zero error. For example, if a mass balance always reads 1 gram before you put anything on it, all your measurements will be 1 gram too heavy. Okay, so you could think about what you would do with that. Okay, so once again, pause the video, bring up the picture that I have of the revision guide. If you have an older sibling or you've already actually bought the revision guide, you can just have a quick look at page 5 and make some additional notes. That'll probably take you about another 10 minutes. Okay, so pause that and do that now, please. Okay, so one of the other things that you need to do is when you're using data in science, you always have to put it into its standard form. Okay, so what I'm going to go through with you now is I'm going to go through what the standard unit is for each of the common measurements that you're going to do in science. So, for example, mass is always measured, slightly out of line, sorry, in kilograms. Okay, so you could just write that next to it. Mass is measured in kilograms. Length, okay, is always measured in, let's see what we've got here. What would that be? It would be meters. Okay, so just go down. Length is always measured in meters. Time is always measured in, where was it? Seconds. There it is. Now, temperature, bit of a tricky one. It's measured in the unit called Kelvin, but that said, you will probably come across it more regularly as degrees centigrade. Just for your information, Kelvin, well, whereas degrees centigrade we think has 0, which is the temperature of freezing water, 100, which is boiling water, and things like that. Kelvin actually goes all the way down to absolute 0, okay, which is minus 273. So 0 degrees Kelvin is minus 273 degrees Celsius. So freezing, so 0 degrees Celsius, is 273 degrees Kelvin. Okay. To be completely honest, you probably won't come across that one, so it's just an information one there for you. Okay, so during physics, another one you will come across is momentum. Momentum is mass times velocity. So mass is measured in kilograms, velocity is measured in meters per second. So momentum is a combination of the two, kilograms, meters per second. Acceleration is a measure of how quickly an object changes its velocity. So, say for example, you've got an object that's going fast and then it slows down, then its velocity is changing. And how quickly that velocity changes is its acceleration or deceleration. So it's meters per second, which is meters per second squared. Right, power. Now, power is a measure of the rate at which energy gets transferred from one kind into another. So say, for example, we had a car, and the car turned its chemical energy, so its petrol, into kinetic energy, movement, and it did that really quickly, probably in like a sports car. That is a measure of its power, and power is measured in watts. Energy, now you will know this from your unit you've just done with me. Energy is measured in joules. Work. Now, this is a difficult one. Work is a measure of energy, but it's a measure of how much something is based on how much it moves. Okay, it's a bit of a tricky one, this one. But work done is how much energy is transferred. So that's actually also measured in joules. And then the last but not least, this one you won't come across right until the end of year 10 or well into year 11, magnetic flux density. So by default, if you've been paying attention, it's the last one left. It's measured in something called Tesla. Okay, that's basically how strong a magnetic field is. Okay, so can you please pause the video and make sure you've linked up the quantity with its standard unit. Okay, pause the video and do that now, please. Okay, welcome back. So one of the other skill sets that you need is learning how to write things in standard form, so scaling for small and big quantities. So, for example, if we have 1,000 grams, that is 1 kilogram. Now, if we look on here, kilo means 1,000, okay, 10 to the 3. That means it's 1 with 3 noughts. Now that one's already there. So basically not 10 and then 3, because that's 10,000. Okay, it's basically the first number plus however many zeros. Okay, so kilo means 1,000. Mega means million. All right. So what we can do is we can do these conversions. Now, really, you always need to make sure things are in their standard form. So what we had on the last page, if I'm talking about, say, a length, okay, so we know length is measured in meters. So if I talk about 10 kilometers or 10 kilometers, what am I saying in meters? Well, it's 10,000 meters. Now, it should always be in standard form when, in that form, in its standard unit when you're doing it in an exam. Okay, so if you had a car travels 10 kilometers, your brain instantly needs to think, right, I've got to put that in meters. So that's 10,000 meters. So let's try a couple of examples here. When doing calculations, you should always convert it to its standard unit. So therefore, 780 grams becomes 0.78 kilograms. Okay, now, so we had 78 grams, that would be 0.078 kilograms. Okay, now, how do we actually go about writing this? So, kilo is this one here, it's 10 to the 3. So it would be, just quickly write it in for you, a 1 with 1, 2, 3 zeros. That's 1,000, okay? 1 times 10 to the 3. Million is 1 with 6, so it's a million. So you've got your 1 and then your 6. A giga is 9. Again, you can see that's would be 1 giga something. So for example, we're talking about waves, which are the frequency, which is measured in hertz. We'd say that'd be 1 gigahertz or gigahertz. Tera is 1 to the 12. So you can see 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we're talking about the frequency of waves again, we'd say that's 1 terahertz, 1 to the 12. Okay, so these numbers can also go the other way, not just very big numbers, but also very, very small numbers. So say, for example, milli. Okay, you will have come across possibly millimeters. Remember, there's 1,000 millimeters in 1 meter. So that would be 0.0001. Okay, so there are 1,000 millimeters in 1 meter. A micrometer would be another 3 zeros. So that's a micrometer. And then you start getting smaller and smaller in the other way, nanometer and so on and so forth. So what I would like you to do is try a couple of these. 0.04 MA. Now lowercase, is that going to be mega or milli, do we think? Okay, capital M, what do you think that could be? So write down these. I'm just going to move that one up for a moment so you can actually see it. And this one as well. What I want you to do is write these down in their standard form. Okay, so let's see how we get on. Okay, off you go. Okay, welcome back. So this is what you should have got. So 0.4 milliamps is 0.0004 amps. That's what we measure current in, electric current, which you'll do in our next topic. 4.7 megawatts, remember mega is million, so that's 4,700,000 watts. 1.8 gigahertz, remember giga is to the power 9, so 1 there, and then 800 million hertz. Okay, so 1.8 gigahertz is that number. 0.07 kilojoules. Now remember, kilo is 1,000, so 0.7 would have been 700 joules. 0.07 is 70 joules. And then finally, 12 teravolts is 12 with 12 zeros after it. Okay, so that's how you would scale it up. So your second thing I would like to make a few notes on is how you actually use these units and equations. So I'm going to give you another 10-15 minutes, and I'd like to use page 8 in the revision guide, which again I'm going to photograph and put on the chat for you. And I'd like to make a few notes on that, please. So you could do it as bullet points or spider diagrams. It's probably worth copying out the table with the prefix and the multiple of the unit, okay? Because that hopefully will get you thinking about how you actually use that. Okay, right, so pause the video and do that now, please. Okay, year 9. So coming back to our task, what I would like you to do now, these are the answers to the first task. So, reproducible. When something is reproducible, a second set of readings gained with different instruments or different person. Essentially, what that means is another scientist could say, copy your experiments, maybe not exactly the same way, maybe use a slightly different set of equipment, but still come to the same conclusion that you did. Okay, so that would be that one. Precise, the data is all really close to the mean, to the average. Okay, so if it's precise, that's what it means. Accurate. Now, accurate, if we scroll down here, means it's really close to the true answer. So what that means is, say for example, you had a number that was 3.47892, something really long like that, but the true answer was 5, then an answer of say 4.5, 4.5 would be more accurate than 3.721 because it's closer to the true answer. Okay, closer to the true answer. Repeatable, repeat the readings to check the results are similar. Usually you would do that 3 times. That's something you're familiar with. So repeatable means the exact same experiment can be carried out, and often the results you would get would be the same. Right, resolution. Now this is the word you must get used to using. Okay, so resolution is the smallest change an instrument can detect. So say for example thermometers. An analog thermometer with the alcohol moving up to show you how much it is can only measure to the nearest degree. Okay, but a digital thermometer can measure to every 10th of a degree. So whereas an analog thermometer might tell you it's 10 degrees Celsius, a digital thermometer will tell you, say, a solution might be 10.4 or 10.5. So the resolution of an instrument, such as a thermometer, is like this. And basically, the smaller the resolution, the more precise your information can be. Zero error, we had this one, but just go through it again. The equipment isn't zeroed properly. What that means is it might read 10 grams if there's nothing on it. Okay, so you'll always be over by 10 grams. Okay, so therefore, what would you do to counter this? You would always have to minus 10 grams from your result in order to get your true value. Okay, your accurate value. Right, anomalous result. We touched on this last week. An anomalous result is a result that does not fit, whoops, move that up, fit with the pattern, okay? And you saw that on the graphs. A random error, unpredictable differences caused by things like humans. Do not put human error ever in an exam. It will score nothing. Random error is the word you would use, okay? It can be caused by things like human mistakes, but it could also be caused by, say, a gust of wind blowing in the window and altering the temperature of the room, therefore affecting your results. It could be caused by unexplained spikes in radiation. It can literally be caused by anything, okay? So random errors are unpredictable differences caused by pretty much anything. And a systematic error is the measurement is going to be wrong by the same amount each time because there is something wrong with your system. So it won't give you the true value. Okay, so that pretty much brings us to the end of today's lesson. So I've talked for 20 minutes and you've had a little bit of time to have a go at this and make your notes from your 2 pages. So hopefully that's pretty straightforward. I will try and put another assignment in a few minutes to help you try and get your head around this. So good luck and I will see you later.